Hello out there and welcome to today's class. Today we shall be taking a look at physics. And the topic for us is current electricity. Okay, current electricity. Now, what is current electricity? Current electricity basically is the movement or the flow of electrons in an electric what circuit. Okay, the movement or the flow of electrons in an electric what circuit. Okay, now what is an electric circuit? An electric circuit is the path, okay, for the flow of current, the path for the flow of current. Okay, all right, this is an electric what circuit. Okay, now this is called the ammeter, measures the what, the value of current. This is the voltmeter, it measures the value of the potential difference. Now take note, the ammeter is connected in series while the voltmeter is connected in parallel. Now this is the resistor. The resistor is constructed to give a value or an amount of resistance. Okay, now this is called the rheostat. The rheostat is a variable resistor, a variable what resistor that controls the value of current by either increasing or decreasing the resistance. Okay, now this is called the switch or the key. The switch or the key can either make or break what an electric circuit. As it is now, it is an open circuit. You can see that what it is open. All right, then if it's done like this, it becomes what, a closed circuit. All right, now this is the battery or the key, the battery or the cell, beg your pardon, the battery or the cell. Okay, so it supplies what's the energy that maintains the flow of current in an electric what circuit. All right, now quickly let's move on to Ohm's law. Now, what is Ohm's law? Now, I want us to first understand that Ohm's law talks about the linear relationship that exists between current and potential difference. Okay. Now, Ohm's law states that the current that is passing through a metallic conductor is directly proportional to the potential difference across its ends, provided temperature and other physical conditions remain what, constant. Okay. Now, mathematically, what Ohm's law is talking about is the potential difference directly proportional to what's to the current. Now, to get rid of this sign, what do? I will introduce a constant. Okay, so V is equal to what? IR. So R there is the constant that I introduced, and it is called what? Resistance. Okay, it's called resistance. All right, now what is the unit of resistance? Okay, the unit of resistance is in ohms. Okay, and this is a symbol for ohms. Okay, now another thing you must understand under Ohm's law is the fact that it is not all conductors that obey Ohm's law. Okay, it is not all conductors that obey Ohm's law. Now those conductors that obey Ohm's law are called ohmic conductors. Ohmic conductors. A ohmic conductor is a conductor that obeys Ohm's law. Okay, examples are metals. Okay, we have metals, we have resistors. Okay, please take note of the fact that what, it is not all resistor. Okay, it's not all resistor that obey Ohm's law. Okay, now those conductors that do not obey Ohm's law are called non-ohmic conductor. Okay, so non-ohmic conductors are conductors that do not obey Ohm's law. So take note of this: non-ohmic conductor. So non-ohmic conductor are, or non-ohmic conductors rather, are conductors that do not obey what? Ohm's law. Examples are your okay, we have your a filament lamp. Okay, a filament lamp. All right, we have thermistor. We have thermistor. Okay, and then we also have some semiconductor devices such as diode. Okay, diode is part of them, and then you have your transistors. Okay, so transistors, all these are under the what? Under the non-ohmic what? conductor. Okay, now from here, now looking at the diagram on the board, now you have three resistors that are connected in series. Okay, now I want us to understand something here quickly. When resistors are connected in series, the same amount of current flows across each of the resistors. Okay, but the potential difference across each of the resistors, okay, are not the same. So what it means is that when resistors are in series, current is the same, but potential difference is not the same. Let's take note of this. So please take note of this. Current is the same across each of the resistors, but potential difference is not the same. I'm talking about for resistors in series. Okay, and then how do we calculate for the effective what resistance? Effective what resistance is equals to what R1 plus R2 plus R3. Now, if we have more than what three resistors, of course we continue like that. Maybe we have up to five resistors. It's going to be what R equals R1 plus R2 plus R3 plus R4 plus R5. Okay. Now let's take a look at resistors in parallel. Now, what happens when resistors are connected in parallel? When resistors are connected in parallel, currents across each of the resistors are not the same. So they don't have the same current. But the potential difference across each of the resistors, okay, is the same. So they have the same potential difference, but different current. But in series, they have the same current, but the potential difference is not the same. All right? So let's take note. Current is not the same, but potential difference is the same. Okay, so how do we calculate for resistors in parallel? It's like this: 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so this is how you calculate for resistors in parallel, right? Now, let us take a look at cells in series. I'm having three cells in series, okay? Every cell has its own EMF. That is what the electromotive force, and there is what an internal resistance, okay? Now, what is EMF? Okay, that's electromotive force. This is the potential difference at the terminals of the cell when the circuit is an open circuit, okay, or when it is not supplying current to the load or to the external resistor, okay. And now, how do you now calculate the effective EMF, okay, when cells are arranged in series? E equals E1 plus E2 plus E3. Okay, so for you to calculate the effective EMF when they are in series, it is E1, E equals E1 plus E2 plus E3. Okay, what happens when cells are in parallel? Okay, we're still going to apply 1 over E equals to 1 over E1, 1 over E2, 1 over E3. Okay, that's the question. Now, let me say this quickly. When cells are in parallel, okay, when cells are in parallel, now every value of the EMF, okay, is the same. Am I communicating? So it means if here is, let's say 10 volts, here too will be 10 volts, even if you are not given, okay? So long as they say that the cells are in parallel and there are 3 cells or 5 cells, the value of each of the EMF for all those cells will be the same, all right? So if here is, let's say, 10 volts, here will be 10 volts, here will be 10 volts. Now, to now calculate the effective EMF of cells in parallel, it's going to be E equals E1 or E2 or E3. Okay, so it means the effective value of the EMF is equal to 1 of the EMF of the cell. Why? Because they are all the same. So please do not forget, when cells are in parallel, okay, the effective EMF is equal to just 1 value of the EMF of the cell, not for you to be doing 1 over E1 plus 1 over E2 plus 1 over E3. No, that is not how it is being done when cells are in parallel. All right. Now, from here, I want us to quickly look at this. Let's look at this. Now, the EMF of the cell is equal to the terminal PD, that's the terminal potential difference, plus the lost volt, or the potential difference across the internal resistor. Okay. Now, note from here, from Ohm's law, that V is equal to what? IR. So therefore, small v is equal to I small r. Don't forget, R stands for what? The internal what? Resistor. Okay, or internal resistance, as the case may be. Beg your pardon. Now, my E is equal to V here is IR. Small v here is I small r. Okay, so my E equals I is common. So I'm having I bracket R plus this. Okay, now if I want my I to stand alone, I'll be having R plus R. Okay, over what's R plus R. So this cancels this. I equals E over R plus R. Now, I want us to take note of this particular formula, because we shall be needing this particular formula when we start solving what questions. Okay, so now let's look at question number 1.